Okay, so welcome everyone. My name is Máté Karácsony. I'm a PhD student from Eötvös Loránd University, and I would like to show you today some details about the research I have made in Sweden at Chalmers University of Technology. So let me start with the resolution of this highly mythical title, namely Zeldspar, the Road to Epiphany. So what Zeldspar is? To understand this, we need two other things. First, we have Feldspar, which is an embedded domain-specific language. It's completely written in Haskell, and it generates standard C99 source code as an output. It's targeted for digital signal processing, so most of its abstractions are related to vector computation somehow. I would like to emphasize actually the support for pool vectors. Pool vectors are usually represented with two attributes. First, they have a length, and second, they have a function, actually an indexing function, that maps a value for each index for the whole length of the vector. And the magic is that if you have operations on pool vectors, then you can combine these operations using a regular function composition of their indexing functions. So actually you can eliminate intermediate data structures and temporary vectors and fuse multiple loops together. And so you can write relatively efficient signal processing applications. So this is one thing we need, and the second is Ziria, which is also a domain-specific language, but it's not embedded. It has a standalone compiler, which is partly written in Haskell. It's actually a product of the Microsoft Research Lab. It was created to help the development of Wi-Fi physical level transmission and so on. The most interesting part of it is how it supports the combination of primitive stream processors into longer pipelines. So actually, Zeldspar is the combination of Feldspar and Ziria. So it's a little bit a play with the names. So actually, it's an embedded domain-specific language. It's also implemented in Haskell, like Feldspar. And as the combination gives the idea, it's about digital signal processing pipelines. Okay. Then, what's Epiphany? Well, it's something like this, but it's not really accurate. This is a board called Parallella. It's similar to Raspberry Pi and the other little microcomputers, but it's actually very unique among them, because it has this coprocessor. This is the chip called Epiphany. It's developed by a small company named Adapteva. And the trick is the following. This board has a dual-core ARM processor. It also have a programmable logic unit. It's an FPGA. And Epiphany is actually connected to the ARM through the FPGA, and it implements a grid of RISC processors. These processors are relatively simple. They have only a few instructions, but you can do vector computations efficiently on an architecture like this. So, if you have a closer view of this grid, at each intersection of the grid, you have a complete CPU, actually, with its own interrupt engine, its own local memory, its own DMA engine, and so on. And if we stay with the reality, what I have on this desk is actually the 16-core edition. So the Epiphany chip in this board have 16 cores, and it has 2 ARM cores, so it's actually an 18-core device. Okay, and my research was about to combine these two things. So what I made is I extended Zeldspar to be able to run on this mesh, actually. Okay, so this is the initial language stack what I had. It already contains a lot of libraries and languages on top of each other. So first I will just say a few words about each item. Then I will explain what are my contributions to this stack. So on the bottom of the whole thing, we have this operational a la carte package. This is available on Hackage. It actually provides you a monad transformer that lets you build imperative programs with custom instruction sets. So it's actually parameterizable over the instruction set, and the a la carte name says that you can combine smaller instruction sets at type level to get more complicated instruction sets, and you can have you can easily have an imperative program with this program T transformer over these instruction sets, and actually you can write different interpretation functions for these programs. So imperative EDSL, this package is also on Hackage, provides a lot of different very useful instruction sets, and it provides two different interpretations for each instruction. Actually, you can either run these imperative programs from GHCI in an interactive environment, when you can execute an interpretation that will actually generate C99 code from these. Well, to have a complete language, you need to have some kind of expressions on the top of it, as actually imperative EDSL is parameterizable over the expression language. So raw Feldspar or research savar Feldspar, this is the current version of the language, actually provides a rich expression language with its different kind of vectors and so on. And it also defines two imperative monads to describe stateful computations. The first is the comp monad, which actually adds support for imperative style control structures like branching and loops, and mutable state in form of variables and mutable arrays. And the RAM monad extends further this comp monad by adding support for file I/O, threading, calling external C library functions, and so on. So this is Feldspar. And Zeldspar actually adds means of creating stream transformers and the composition of those stream transformers. I will talk about these operators later in more details. So this is the initial language stack, and I built something on the top of this. Actually, this library is called raw Feldspar MCS, which is resource of our Feldspar with multi-core and scratchpad support. So it actually adds some new language elements to Feldspar to be able to write programs for many core accelerators and to handle special caches and distributed memories and so on. And it actually extends Zeldspar to add the parallel composition that can be compiled to parallel programs on these accelerator processors. And the joke is that actually it reuses again this operational a la carte package to implement these new language features. So I added new monads to describe computations that can be run on the host processors, in this case the ARM. I created a core comp monad that could describe computations that can be run on a single processing unit of the grid in the accelerator, and some types for handling arrays in different local and shared memories, and so on. Okay, but before everybody gets bored and sleepy and something else, I would like to show you a demo which will hopefully work. And it will not be visually spectacular, but if everything is right, we will hear something from it. So it's just a sound test first.
Front, left.
Okay, we have sound. And now the magic. I have an SSH session to this machine through this Ethernet cable. What I typed in is not really important. Actually, I made a demo application and I built it and I started it. So it actually starts a web server on the Parallella, and I can view the page up, hopefully. Yeah. So, if I push the start streaming button, the following will happen. The microphone of my laptop will catch my voice and it will send down to the Parallella into a pipeline, Parallella pipeline, which is running on the Epiphany chip, and it will modify my voice slightly and sends it back to the speakers if everything goes alright. So, well, I hope something happens. No? Then please catch this. Or restart the browser. Uh-huh. Anything?
Did you push the button again?
Well, 5 minutes ago it was okay. Go back and check. It's already running, but I'm going to kill it and restart it. Okay. So it will recompile the whole thing and hopefully it will work. Still have sound?
Front,
Yes, we
right.
still have. Okay, maybe now. So, anything happens? No? That's not okay.
Could it be that the volume of the microphone is too low?
I don't really know. It seems to be okay. Absolutely. Oh well then, I will just continue the talk now and we will try it again at the end, okay? Sorry, that's the... that's how the demo should go. Okay, so, well, the effect that you didn't hear, that it should pitch my voice up with an octave, and that's all, actually. So it's kind of a sound distortion application. And as you can see, it's a little bit complicated, so I'm not really surprised that it not work at every time I try to demo this anywhere. So actually what you can see is I have a web browser running on my laptop, and it has the microphone and the sound output. And I have the Parallella board with its ARM processor and its Epiphany coprocessor. And what happens is that actually my laptop captures my voice and sends it to the web browser, which captures it with the JavaScript Web Audio API application and sends it through a WebSocket to the ARM in the Parallella, and it actually sends it through to another process which is mostly running on the Epiphany, and after the processing is done, it sends back the audio sample which is processed. So it's a relatively complicated thing. Most of it is just actually decoration to get somehow the sound samples into the Epiphany and back from it. Most of these parts are written in pure C and pure JavaScript, but the important part is that the whole signal processing application is actually written in Zeldspar, and it's compiled and linked together as a separate unit, actually. Okay. So, if you look at the Epiphany chip, what I made is that I mapped each stage of this pipeline into a processing unit. So as you can see, most of this processing is actually consists of several stages of fast Fourier and inverse fast Fourier transformation, because the signal is actually transformed from the time to the frequency domain to do the shifting of the pitch. It also involves some kind of filtering and shifting and processing, and I don't know, it doesn't really matter what these elements are doing. It's more like DSP stuff than the compiler stuff. But let's look at this thing, how this pipeline is actually described in Zeldspar. So, what I show here is the actual Zeldspar code that shows the assembly of the pipeline that runs on the Epiphany. And if you look at this carefully, I included here again the figure about the mapping on the Epiphany chip. You can actually see a one-to-one correspondence between the two, so it's very easy to see that which programs are running on which cores. So if you look at how it's assembled, actually I have an operator to combine two smaller programs into a more complex one. Then I can use this on operator to explicitly map a stream transformer into a specified core in the accelerator chip, and I have this kind of parallel composition, which means that I want to combine these programs in parallel. Well, it's a tricky operator. We can actually think that this is simply the parallel version with bars on each end, which is similar to this one, but actually it has to have some information about the communication channel size between each processor cores, as it will communicate through some kind of buffers. So it's something like a mix-fix operator. Okay. So actually in Zeldspar, every elementary stream transformer that can be used to build longer pipelines is looking like the following. If you have a transformer T, it has a type something like this. It's actually a Z monad transformer with an input type, an output type, an underlying monad, and a monadic result type. So if I want to make a picture about it, it looks like this. I can use a take command to consume data from typed as in, and I can emit or produce data elements typed with out, and I can actually use the commands of the underlying monad M by lifting them up into this Z level, and I can make infinite loops to continuously transform the incoming data. So let's see an example. These are the first two transformer blocks, window and S complex, and I made some type aliases to work with these things a little bit easier. So I have type aliases for two different kind of vectors. The dpal type is actually the type of pool vectors in Feldspar. So first I have real samples, which is actually a pool vector of floats, and I have complex samples, which is actually a pool vector of complex numbers. and I have a specialized version of this Z monad where I fix the underlying type of underlying computations into this core comp. So core comp is basically contains all the imperative constructions that you can use on a processing node in the Epiphany. So you have access to mutable arrays in the shared memory, in the local memory. You can have imperative control structures and so on. So I made an alias called core Z to this thing. So if you look at this window function, it's actually some kind of a simple filtering of the signal. It actually works on real samples and also it emits real samples. It doesn't really have a monadic result type. And actually it does nothing, just in an infinite loop always receives an input vector and emits an output vector such it just multiplies each element of the input vector with some predefined coefficients actually. So it's very simple filtering. The zip width is implemented in Feldspar, and Zeldspar actually adds these lift, loop, take and emit constructions to this thing. The second, this S complex, is also a very simple stream transformer, but it has different input and output types. So it works with real samples, but it emits complex samples, as the fast Fourier transformation is working on complex numbers. So actually it's just a conversion. It does a very similar thing like window. In an infinite loop it takes an input vector, then it emits a version where each element is mapped with this flip complex 0, where complex is actually just a constructor of complex numbers, where the first parameter is the rational and the second is the imaginary part. So we flip these two and actually apply it with the constant imaginary part. So it will be a function that creates a complex number from a given real part. Okay, so if we have these two stream transformers, we can fuse them together. Actually, you need to have such programs that have matching inputs and outputs. Actually, if you try to combine the first program with the second, then the first program has to have the same output type as the input type of the second program. And if it's true, you can combine these two programs as this. And the fusion means that this operator will try to match each emit in the first program with a take in the second program. And if it's possible, it will actually eliminate these two instructions and create a single function application from this. And the genius inside this idea, it's not mine, that if you have this pipeline fusion, then you have function application between the processing elements. So you will have automatically vector fusion on the Feldspar level, because you have used pool vectors, and if you are composing pool vectors, then it actually became function application, then the fusion will happen. And if you look at the generated C code, you will see the following. You will have a single input array, you will have a single output array, and you will have only a single loop where actually the multiplication, the zip width, happens. And actually you cannot really see the complex conversion, as the conversion that compiled from this is actually removed during the constant folding phase. So you can see here a plus 0i tag for the complex number. Without the fusion, you would see two separate loops and one more temporary real array. And the first loop would just do the multiplication between the real arrays, and the second loop would do just the conversion between the second real and the complex array. So actually we eliminated a loop and temporary storage this way. Okay, if you have elementary processing units like this, you can specify the mapping of these processors to physical cores. So actually we have this on operator that receives a computation that can be run on an accelerator core, and it receives a core ID, which is actually just a number in the current implementation, and it will return you something like a multi-core Zeldspar computation. We will see this in detail later. But there is a tricky thing here. Well, actually, to communicate between the different cores, we will somehow need to represent the data in the memory. And actually, in Feldspar, pool vectors are described with a length and with an indexing function, but we cannot send these things through the processing cores. So first we need to write the contents of the vectors into the memory. And actually this type, store real samples and store complex samples, are just arrays that can hold the elements of these vectors. So when I have a processing unit that works with pool vectors, then some type conversion will happen that will eventually convert these pool vectors into their memory representations. And those could be transferred between the cores. So core transferable means that it's something that some type that could be serialized eventually. And core transfer type means that this type could be represented as a serializable type as this representation, and I can convert between the two when I'm in this context. So it's actually only a conversion. Okay, then if I have these multi-core programs mapped to each core, then I have this parallel composition operator, which is, in case of primitive scalar values, it's pretty simple. I have a multi-core program 1, a multi-core program 2, and I will have a third program here. And also it needs to obey this rule as the sequential fusion, that the output of the first program must be of the same type as the input of the second. But if you have more complex types than scalars, then you have something like this. This operator is split into half basically, and we have lengths in between. So for vectors you can specify the length of vectors which were transferred between the processor cores. And as Haskell doesn't have support currently to mix-fix operators, it's actually defined with 2 operators, so it's actually just a hack. But if you look at carefully of the type of the second operator, you can see that it's just actually a function application. So these forms are actually equivalent in this way. Okay. So back to the transfer types a little bit and to fusion. We have another 2 processing units like analyze and shift pitch. And analyze is something that creates a complex vector from a complex vector, but shift pitch is a little bit different. Its output can be written with a pool vector computation, actually. So what it generates is basically an array and not a pool vector, but it can take pool vectors to create this output array. And the interesting case is that first, what happens if we try to combine them in parallel? Of course, it's easy because this on operator will convert each pool vector into its store representation. So actually everything will be replaced with the complex sample store here, and the type of the combined program will be something like this, and the data between the cores will be transferred in regular arrays. But what about these other 2 constructions? If I try to fuse together sequentially in these 2 ways. Well, in the first case, you are lucky as analyze has output complex samples and shift pitch has input of complex samples, so it will fuse together into a single loop, but the resulting program will generate an array basically from a pull vector. But if you try to combine them from the other way, it won't really work, because the first process will emit complex sample store, so an array, and analyze wants to receive a pull vector, so this composition is not possible in this way. Okay, so we have this multi-core Z programs over some input and output. How can we run these pipelines? Well, we have this run Z, which receives the pipeline, and 4 other things. If you look at the picture, the following will happen. The pipeline will be mapped into the cores of the accelerator, and they will have channels between each other to communicate. And also, to start and feed this whole pipeline and process the elements that it produces, we need some programs in the host, which is currently, in the case of Epiphany, is the ARM processor. So actually we will have 2 programs. We will have a program that runs in host and creates input elements for the pipeline, along with a flag that this is we are after the last input element or not. It has some role in the termination of pipelines. And we also have a sync program that also runs on the host, and it can process the element that came out at the end of the pipeline. As we need channels to communicate between the host and the accelerator in both directions, we also have 2 size specifications. So in case of scalars, this is unit. In case of vectors, is the length of the vectors which are transferred between the host and the accelerator core. And this whole thing will yield us this kind of multi-core computation, which is actually an extension of the raw Feldspar. So what happens here is that you have your Zeldspar program, then it will be compiled down into appropriate constructions over Feldspar, that will be compiled down into imperative EDSL, and that will be compiled down into regular C code, or it will be interpreted in GHCI. So, a little bit about channels. They have a pretty simple interface. You can create a new channels specifying core IDs. So for example, I can say that I want a communication channel between core 5 and 7, or you can have a special channel which is connected to the host. So there is a special core ID that is the ID of the host, and each channel has a size specifier, and it will actually return you some kind of channel. You can read them, write them, and the channels are closable. So this is the whole channel API basically. And what I need to show is these 3 monads. So I have this core comp, which is actually an extension of the comp monad from Feldspar. And here you can see that basically comp contains the following instruction sets. You can have imperative style control structures, references, which are basically variables holding scalars, and mutable arrays. And I extended the capabilities of comp named core comp, where you can actually stop the processing unit, communicate between these using these core channels, and you have some operations to copy arrays from local and shared memories. So actually this is the type of computations that could be done on an accelerator core, and our core Z was built on the top of this. So host is a similar thing, but it builds instead of comp on the more capable run monad of Feldspar. Run is actually built on the top of comp So you already have the mutable state and the imperative style control structures, but it gives you more. You can create threads, communicate between threads, have file I/O, call external C functions, and do pointer swapping and any other magical things. And I extended this run monad to create the host monad. And actually this is the type of programs that could be run on the accelerator core. So it can also communicate with the cores on the channels allocated earlier, and it can halt the cores, read and write the shared and the core local memories, and it can spawn the computations on the specific cores. And this whole thing is actually wrapped into this multi-core monad, which is like the frame of this whole multi-core Feldspar extension. So if you have a multi-core Feldspar program without Zeldspar, then it looks like the following. You have a computation in this multi-core monad. You have a few allocations of channels and arrays in different shared and local memories, and you can spawn the host computation with this onHost instruction. Then you will have this computation in the host monad. And in the host, of course, you can do the file I/O and anything else I have shown you earlier. And it has this on-core instruction, which receives a core ID and a core computation. And it will spawn the computation on the accelerator core eventually. So, summarizing the monad stack, Feldspar provided run and comp. I extended run with host, comp with core comp, and I created a separate multi-core monad to handle basically the allocations. And this whole thing is built on the top of the program T provided by operational a la carte. Okay, then how can you really run a multi-core Zeldspar program? Well, here is your multi-core Zeldspar program. It's composed from smaller core Z programs into a single big multi-core program. You provide a host program, you will provide two programs that running on a host. One is the source and one is the sink of the pipeline, and you apply this runz, which returns a multi-core computation. So actually runz will translate this program into channel allocations and an on-host call and into several computation spawning instructions. Okay, and how can you run the whole thing? Actually, Feldspar contains two functions, one compile all and one run IO. So if you have a Feldspar program in the run monad, you can easily use this to either compile it or either run it in GHCI. But Feldspar also provides this monad run type class. So if you can convert something into run, then you can use the same programs to run it with their different interpretations. And actually, this multi-core has an instance of monad run. So if you want to run your multi-core Zeldspar programs in GHCI, you can do it. It will actually use Haskell threads to do the parallel processing of the pipeline, and you can compile it to the default architecture, which is x64 with pthread library support. So I can run the same pipeline on my laptop, even in a compiled or in an interpreted version, or if I use this second version, which chooses a different interpretation for the same AST, then it will generate Epiphany specific code, which I can deploy to a Parallella board. And actually I can test and use the same program without any modification on two different platforms. Okay, how many time do I have? 40 minutes. So I have about 5. Or nothing. So, okay. Well, I had a second demo earlier, but as the SDK changed on the Epiphany, I have a newer version than I had in Sweden when I made the compiler. I didn't really have time to prepare the second demo, but I will try to do again the first. And I have two projects related to this whole thing. First is that the fusion operator in Zeldspar is well, needs some underlying theory, because now it works somehow, but we want to create a formal semantics of it. So if anybody wants to join some formal thinking about the fusion operator, that's one project. And the second is that the current implementation of communication channels between the processing cores is really a prototype. So I really want to get more performance out of the board. And this involves some hacking and embedded C programming, so if anyone is interested in that, you can also join me. So as the last thing, I will try to run the demo again. And we will see. Maybe I will cheat now a little bit, because I said that the same program can be run on the Parallella and on a regular laptop. I will try to run it now on this machine. And this is not the Parallella, but my local host. Yep, something. I have an idea. No, everything seems fine. Well, this way. It's something with the infrastructure, because I can hear it back from the speakers of this laptop now. It's just not too loud. So if you want to hear what it does, you can come here. I'm actually finished. So. Maybe something like that, but.
Then you have to select the big microphone, like output.
Well, I have only one device for capturing audio,
yes,
and the only thing I can use here in set here is kind of
the output.
Front left.
some kind of audio routing stuff between the processes. I don't.
Project.
Yeah, maybe, but it's more like a configuring sound under Linux. Okay, so that's it. I hope you enjoyed it. I'm a little bit sad about that you can't hear the demo, but you can hear it after. Oh, something? No. Okay.
Do you have questions?
Yes, so you said you rely on fusion, I mean the performance characteristics relies on fusion, and how do you check whether fusion happened or not?
Well, should I repeat the question? Yes, so the question was that how can I see whether the fusion happened or not? Actually, you can see it on the type. If you are using transformer blocks that are emitting and receiving pull vectors, it's sure that you will have the fusion at that point where you connect the two processes. It's that simple, actually. If you have anything else than a pull vector, you will not get the fusion. It's completely visible in the type. But of course, it's not possible to write any algorithm with just pull vectors. So this is the trick here. As I had this shift pitch part of the computation, it's shown that, for example, that could not be written using pool vectors. So, yep, so this.
What's the relation between this project and Obsidian, if you know that? It's also
Yes.
Chalmers and the wrap-up project, which is done in universities.
Yes. Okay. So the question was, what's the relation of this project with the Obsidian and the REPA projects? Actually, I talked a lot with the maintainer of Obsidian, Bo Joel Svensson, if I'm correct. So, well, Obsidian is for GPUs mostly, and this kind of stuff is working on a relatively similar architecture, because we also have a host processor, some kind of accelerator with many cores. But as far as I have seen, in Obsidian you define a single kernel program in the end, and all of the cores are running the same program, and you don't really have choice about it. And you, as far as I remember, Obsidian doesn't have the tools for writing the host part of the program. So you write only the kernel in Obsidian, but you can't really assemble a complete program in that language. But in this case, you can actually write the whole program just in Zeldspar, and this is why I have this architecture, that I have a separate process for the web server and I have a separate process for the signal processing, because this whole process is linked from the source code of the Zeldspar. So actually it's a completely independent program. Of course it contains some C library calls to do the communication with the other process through Unix name pipes. But that could still be done from Zeldspar level, because Feldspar has support for calling external C functions.
But REPA has developed a more advanced fusion system they call flow fusion, which is has bigger expression power than string fusion. So they analyze the ASP instead of relying on rewrite rules. I mean, string fusion usually relies on string.
Yeah, well, actually, the vector fusion is provided by Feldspar, and it actually relies on the rewrite rules. Yes, so Haskell will actually create a function composition, but the string fusion here in Zeldspar, actually this operator actually does a more tricky thing. So the magic of stream processor fusion is hidden inside this, and unfortunately this is the part where we need more theory under the whole thing, because now we have some implementation that seems to be working in most of the cases, but in general, if you have programs like this with arbitrary number of takes and emits and loops and I don't know, it's not very trivial to match each take to an emit in the general case. Of course, in most of the cases, in the practical cases, they will align. So it's not really a problem. Any other questions?
What's the most complex example of what you done like this?
Well, actually, I think this audio processing stuff, and I also have an implementation of the blah 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 blah. It would be the second demo. So an implementation of the blowfish encryption as a stream cipher. So what's the cool thing about this is that actually the code is very similar to the mathematical description of the cipher. So that's a very cool stuff. But I think in sense of complexity, the audio processing example is much more complex than this one.
So if there is no more questions, then thank you again. Okay, so the talks are over, and now we will present the project that we will work on. So we taught 2 projects already.